Hey, what's going on guys? Tanmay here for Simple Snippets, and in this video we are going to perform the implementation of delete node operation in a AVL tree using a recursive approach. Now before we proceed with this video, in case if you have missed any of the previous tutorials in this playlist in this DSA course, please do check out this entire playlist because this is like a continuation of AVL tree topic. We've already talked about what is a binary search tree, what is AVL tree, what is balancing, the insertion in AVL tree, and also implemented the insertion. And we've also theoretically discussed what is deletion in a AVL tree and how the balancing happens. So all these topics are already covered. If you have already watched all of them, this video is going to be very easy to understand. If not, you will still understand this video, but there will be a little bit of difficulty. Okay? Alright, so now that the initial introduction is done, let's talk about today's video. So today we are going to write a C++ program to implement the delete node operation. So that is what implementation means, that is converting the theoretical operation into a proper practical code and to check whether the code works or not without any errors. Okay, so that's our end goal. So by the end of this video, we will implement this delete node operation. Now on the left hand side, as you can see on the screen, we have the code for binary search tree delete node operation, and this is a recursive approach. So this is something that we have already seen in the tutorial, which you can see on the screen. I will also link this video in the video description. And this is the entire pseudocode, which is step number 1, 2, 3, 4 and 5. So 5 steps pseudocode for delete node using a recursive approach. Okay. And on the right hand side, you can see we have AVL tree delete node operation, and again the pseudocode for AVL tree. However, the first 4 steps are same as binary search tree deletion, which means that step number 1, 2, 3 and 4 are gonna be exactly same in the delete node operation of AVL tree. That makes sense, right? Because AVL tree is nothing but a binary search tree only. However, AVL tree is having an extra property that it is always balanced. And to keep that always balanced property, every time you delete a node, we have to check whether the tree has become imbalanced or not. And hence, we have this step number 5, 6, 7, 8 and 9 extra along with these first 4 steps of the binary search tree. Okay, so in the comments you can see I've written first 4 steps same as binary search tree deletion. So these first 4 steps are gonna be as it is, and after that you have step number 5, 6, 7, 8 and 9, which will check whether the tree is still balanced or not after you delete a particular node. So the first 4 steps will do the deletion, then you'll get the balance factor over here. We'll talk about this in a minute. Then you'll check which kind of imbalance has happened from step number 6, 7, 8 and 9, and lastly we will say return R because it is a recursive approach. So you can see the name of the function or name of the operation is delete node. Programmatically we are going to return a pointer of type tree node or node if you've written your class with the class name as node. This function is going to take 2 parameters or 2 arguments. First one is the root node and the second is the value of the particular node that you want to delete. Okay. So this is a little bit of overview, and right now these steps will not make clear sense as of now. That is because we still have to see the different scenarios which happens when it comes to imbalance after you delete a particular node. So we'll see that in a minute. But I just wanted to give you an overview and comparison between the delete operation of a binary search tree versus the delete operation of a AVL tree. And from this entire screen, the take is that delete operation in AVL tree is exactly the same, with some extra steps which are regarding with the balancing of the entire tree. Alright? Okay. So now that you've understood that, let's understand these 5 steps which are there in yellow, and let's see what do these things do. Okay? So step number 5. So let's say the first 4 steps are done. So these are the first 4 steps which are same as binary search tree deletion. So first 4 steps will actually delete the node. Okay? So step number 1, 2, 3 and 4. Once executed, it would mean that the node is deleted. So let's say we have this tree over here. Let me draw the tree below. So let's say we have a tree something like this. Okay. Let's say the value is 20. This is 30. This is 10 and this is 5. Okay. So let's say you perform the delete operation and first 4 steps are done, and now you've deleted this node 30. Okay. So after this, we will perform step 5. So step 5 is where we get the balance factor. So this variable bf will hold the balance factor value, and this get balance factor is nothing but a function which we will have to write, and that would give us the balance factor of the current tree. So this R is nothing but this root node that we will pass, and you can clearly see that this is imbalanced, right? So this will give 2 as the balance factor in this scenario, because if you calculate the balance factor of this tree, this is the left subtree LST, whose height is going to be equal to 1, and for the right subtree we have nothing, so the RST is going to be equal to -1. So 1 minus -1 is going to give us 2. Okay, and this calculation is what this function is going to do. I will show you the code of this function also. We have already covered this in previous tutorials, so we will go a little fast when it comes to getting balance factor, but I'll show this entire function in a minute later on. But once you get this balance factor, this BF variable will store 2, and now these 4 steps, steps number 6, 7, 8 and 9 are for 6 different scenarios. So these are 4 steps, 1, 2, 3, 4, which represent 6 different scenarios. So we have a if, else if and else if control statement, which will represent the 6 different types of imbalance. Okay, and the point number 6 and point number 8 are collectively for one particular type of imbalance, which we will talk about. And as I mentioned, right now it will not make sense, which we will talk about. And right now, as I mentioned, it will not make sense, but when I show you the diagrams, it will be very clear. But understand that these 4 steps from 6 to 9 are for the 6 different variations of imbalance that can happen when you delete a node in a AVL tree. Okay, so these are the only 6 different scenarios that will happen, and each of this condition is to check whether those scenarios occur or not. And depending upon which scenario happens, we will either perform right rotate, we will either perform left right rotate, that is LR rotation, or we will perform left rotate only, or we will perform right and left rotate. So again, these are individual functions which I will show you the code for. We have again already covered all this in previous tutorials, but we will definitely see these functions also, don't worry. So let's understand these different imbalance scenarios that happen when you delete a node. Okay, so only then this 4 steps will be very clear. Let's diagrammatically try to understand them. Okay, so as I mentioned, there are 6 different cases that will happen when you delete a particular node from a tree, and it can be divided into 2 parts or 2 categories. So either you delete from the right subtree. So when you delete from the right subtree, things would look something like this. Let's say this is the tree, okay, and you're deleting from the right subtree. So for this particular node, this is the left subtree and this is the right subtree. So when you delete this node, you're deleting from the right subtree, correct? Similarly, another case can be something like this, right? And this is the left subtree, LST, and this is the right subtree, RST. So when you delete this node, you're deleting from the left subtree, correct? So when you delete from the right subtree, the balance factor usually becomes 2. And when you delete from the left subtree, the balance factor becomes -2. So you'll see that in a minute. I'll show you with the diagram. But let's see the first case, which falls in the category of deletion from the right subtree. So I'm showing you 2 cases. That is because in both these cases, we are going to do a right rotate only. And let's see the first case. So here's the first case where we have this AVL tree and you have to delete the value 40. So when you delete the value 40, you'll calculate the balance factor for every node, because after deletion or insertion in an AVL tree, you have to again calculate balance factor for all the nodes so that you can figure out whether the tree has become imbalanced or not, right? And in this case, for this node, which is the root node over here, R, or let's say it is N1, the balance factor has become 2 because the left subtree is this, whose height is 1. I hope you know how to calculate the height of a tree. We have a separate tutorial on that. I've also shown a separate tutorial on calculating the balance factor also. So the formula for that is given by, let's say this is BF is given by height of left subtree minus height of right subtree. Okay, and this balance factor has to be in the value of -1, 0 or 1. If the balance factor goes below -1, that is it becomes -2, -3, -4, or if it goes above 1, which is 2, 3 or 4, then you can say that the tree has become imbalanced. Okay, so I hope you all know all these concepts. So when you calculate the balance factor for node N1, the balance factor becomes 2 because left subtree is 1 and the right subtree has nothing, which means it is -1. So 1 minus -1 is going to give you 2. Okay, so now when this becomes 2, you can see this comes under this category, deletion from the right subtree. You're deleting 40, which is towards the right of 30. So that's why it is coming in the deletion from right subtree category. and in that case the balance factor always becomes 2. So this is imbalanced, and looking at this you can see we are performing a right rotate because it is a left imbalance, LL imbalance or LL case. So in that case, remember what do? We do a right rotate. I hope you know the different rotations. We've discussed them thoroughly in a separate tutorial again. So in that case, this N1 root node is taken down and this center node comes at the top. So you can see 20 goes to the top, 30 goes to the bottom, and now it is a proper balance tree. Alright. So this is a right rotate scenario. Let's say there is one more scenario where the tree looks something like this. Over here, you can see we have one more extra node over here. That is the only difference. In this diagram, we did not have any node over here, but over here we have this node. So it's not looking like a typical left-left imbalance, however it is. So when you delete the node 40, you're deleting from the right subtree. So again we have this unbalanced tree. The balance factor for root node N1 becomes 2 because for the left subtree we have all these nodes with the height of 1, and for the right subtree we don't have anything, which means the height is -1. So balance factor of course is going to be 2 because 1 minus -1 is going to give you 2. And again you'll do a right rotate. But this time you also have to arrange this number 25. So when you do a right rotate, what happens? N1 comes down, 20 becomes the new root node. So 20 becomes the root node. The right child becomes this N1 30, N1 is over here, and 10 becomes the left child of 20. So remaining value 25 should be going to the right of 20. So you go to the right, but 25 is smaller than 30. So you have to go to the left. So it becomes the left child of 30. Okay. And now this is a balance tree. If you calculate the balance factor for all the nodes, it is going to be coming in the range of -1 to 1 only. And in both these scenarios, you can observe that the balance factor for the top node was 2. Correct? But the second condition, let me show you the code which had those 4 different conditions. So if you see the first if condition, so the condition is if balance factor is equal to 2, which means that the balance factor of N1 is equal to 2. Yes, it is true. In both the cases, the balance factor is 2. And the second condition is we are saying get balance factor of R of left. R currently is going to be N1. What is there to the left of N1? We have, let's say 20. Let's name it N2. So we are taking the balance factor of N2 also. And we are saying if the balance factor is greater than or equal to 0. So for N2, the balance factor we've calculated is 0 over here and it is 1 over here. So it is satisfying the second condition also. That is the balance factor of R of left, which is nothing but N2 over here, has to be greater than or equal to 0. So it is 0 over here, it is 1 over here, which is again satisfying this condition also, the second condition. And both the conditions have to be true because there is an AND in between. And when that happens, in that scenario, you can see inside in the if we go, we are doing the right rotate. Correct? So this case 1A and 1B, in both the cases, we have to do a right rotate. And that is the condition which you can see in step number 6. Okay? So I hope you understood that step number 6 and the condition inside it. And when that condition is true, when both the conditions, that is the balance factor is 2 and the balance factor of the left node is greater than or equal to 0, in that case we will do a simply right rotate and you will get a balance tree. Okay. So let's see the third case where the balance factor of the root node, that is N1, is 2. However, the balance factor of the left child is not greater than equal to 0. Okay. So this is case number 1C. Over here, this is how the structure of that AVL tree looks like. Now you want to delete 40. So when you delete 40, you are basically deleting from the right subtree only. This is N1, this is N1. Okay. So when you delete this, our AVL tree looks something like this. And over here now you can see the balance factor for N1 is still 2 because this is the left subtree. If you calculate the height of this left subtree, you will get 1. There is nothing to the right. So it means 1 minus -1. So ultimately balance factor is 2. But if you calculate the balance factor for the left of N1, who's there to the left of N1? We have N2 over here. If you calculate the balance factor of N2, the balance factor is coming to -1 because we don't have anything towards the left. So height is -1. We have one node to the right, and when we have only one node to the right, the height is going to be 0. So -1 minus 0 is going to give you -1. So this does not fall with the first if condition, which is step number 6 you can see. In step number 6, the condition is the balance factor has to be equal to 2 for the root node N1 and the balance factor of the left of this root node, which is N2 over here, has to be greater than or equal to 0 but now the balance factor is less than 0, which is -1. So for that we have the next else if condition, which is point number 7, which says that if the balance factor is equal to 2, yes, it is 2 for n1, which is the root node. However, and in the AND clause we are saying, and if the balance factor of the left child of this node n1, who's the left child of n1, it is n2. If the balance factor of n2 is less than 0, which is nothing but -1, so you can see it is equal to -1. If it is equal to -1, in that case, we have to do a left-right rotation. So if you go inside, because now the point number 7 is going to be true, right? In that case, you can see we have two steps, which is first we do a left rotate and then we do a right rotate. And clearly from the structure also you can see that this is a left and right imbalance. So in that case you do a LR rotation. And after you do a LR rotation, this is the structure that you get, because 25 becomes the new root node. Okay? Alright. So I hope you got the first 3 cases where you're deleting from the right subtree. Out of the first 3 cases, the first 2 cases are where you do a simple right rotation, and the third case is where you do a left-right rotation. Okay? So now let's see the remaining cases where you delete from the left subtree. So in the remaining 3 cases, the first 2 cases, that is 2a and 2b, again are similar because we only do a left rotate over here. And let's see them quickly. So in 2a, let's say you're deleting 10, which means you're deleting from the left subtree. Let's say this is n1. After deletion, this n1's balance factor becomes -2. You can see in all these 3 cases, the balance factor for the root node n1 is going to be -2 only. And you can clearly see this is a right-right imbalance, so you'll do a left rotate. So n1 will be taken down and 30 will become the new root node, and then you get a balance tree. Similarly in 2b also, when you want to delete this node with the value 10, you're deleting from the left subtree, you get this structure, which is again a left-left imbalance. Again you do a left rotation and you get this structure. Now these 2 conditions are satisfied with the point number 8, which is the else if condition 8. Now if you see the point number 8, which you can see on the screen, in the else if condition, what do we have? We have if the balance factor is equal to -2, that is the first condition. And then we have an AND clause, we say and if the balance factor of the right of the root node, what is the right of the root node? So if this is n1, which is the root node, the right child of n1 is, let's say this is n2, and over here also this is n2. So we are saying get balance factor of right of the root node. So you can see get balance factor, we are saying r of right, and if that balance factor is less than or equal to 0. So in both cases you can see n2 and n2, the balance factor is -1, which is less than 0. Over here the balance factor is 0, which is also following the condition. So in both these cases the conditions are true. The first condition is, of course, the balance factor has to be -2 for the root node n1, which is true over here and over here also. And the second condition is for the right child, the balance factor has to be -1 or 0, which means it has to be less than or equal to 0. And when both these conditions are true, in that case we simply have to do a left rotation because it is a right-right imbalance. Clearly you can see it is a right-right imbalance. After you do a left rotation, you get these structures which are balanced. Okay? Alright. So the third case, when you're deleting from the left subtree, is little different because in that case we have to do a right-left rotation. Let's see that case. So in this case, when you delete 10, you get this structure where you get the balance factor of the root node n1 as -2, but the right child, which is n2, gets the balance factor of 1. So you can see this does not fit in the step number 8, correct? Because for step number 8, the balance factor of the right child has to be less than or equal to 0. But this is 1, which is greater than 0, correct? So for that we have again point number 9, where balance factor of the root node is -2 and the balance factor of the right child of this root node is equal to 1. In that case, you can see we have a right and left imbalance. So in that scenario, we do a RL rotation, and after that you get this structure. Okay? So I hope you know when we do a left rotate, when you do a right rotate, when you do a LR and RL rotation. This is something that we've already discussed previously. I just wanted to show you these 6 different cases which are handled by these 4 conditions. The reason why we have 6 different deletion cases but only 4 conditions is because 2 of these conditions handle 2 cases each, right? So 1A and 1B, we have only 1 condition. 2A and 2B, we have only 1 condition, and remaining 1C and 2C, we have 2 more conditions. So that's why we have 4 if-else control statements which are handling these 6 cases together. Alright? Okay, so now I hope you've made sense with those different conditions which are handling the rotations in the AVL tree. So now that you've understood this 6 deletion cases and also the pseudocode for performing the rotations, let's actually dry run the entire code at least once so that you get the full understanding of the working of AVL tree deletion with the help of diagrams, and we'll see step by step with the proper recursion to understand the working. Okay, so as you can see, we've started with the AVL tree delete node function recursively, and for the first 4 steps, as I've already mentioned, it is going to be exactly the same as the binary search tree deletion. But let's go quickly through the entire pseudocode because it will give you a good recap and good revision of the BST delete code operation. So this is the delete code function. It will take tree node R, which would be basically the root node that you pass with the very first call when it comes to recursion, and int v is nothing but the value that you want to delete. So let's say over here the value that you want to delete is 40. Okay, so we entered 40. And R is going to be nothing but N1. So over here on the diagram, we've drawn a basic AVL tree because this is balanced as of now. And the one that you want to delete is the node N4 because it has the value 40. Okay. So we will enter the value that you want to delete. And then we will go inside this tree and search for this value, arrive at that particular node and then delete that node. So that's the goal. So the value that you want to delete is 40, which is actually N4. Correct? Alright. So the first function call would look something like this. Over here you can see this is going to be the very first function call and it will happen from the main function. We will say obj.root. So right now the root node is nothing but N1. So basically this is N1, which is equal to, so on the left hand side on the LHS we have N1. We're saying obj.root and this obj is nothing but the object of class AVL. Okay. So when it comes to programming part, when it comes to the implementation side, in the C++ program, we will create our own AVL class, which will have its own root node pointer. Remember, we are using C++ programming and we are playing with pointers. Hence, we have this syntax as *r. Correct? So this root is nothing but a pointer which is pointing to the object of type tree node. So this tree node is again our own custom defined class, which has 3 data members, which is the left pointer, the right pointer, and the actual value. And then you create the object of these different classes. Okay. So for the first call, the first function call, we are saying obj.root on the left hand side, and on the right hand side you say obj using the same class to call the function, that is the member function delete node. Inside that, the first parameter you can see over here, R, is nothing but we are passing the root node, which as I mentioned is already N1, comma the value that you want to delete, which is 40. Okay. Alright. The reason why this delete node function is on the right hand side is because it will return us the pointer back again. So you can see the return type is tree node star. So this delete node function will return us the pointer of type tree node, and on the left hand side also we have a pointer root which is also of type tree node. So that's why we need something on the LHS to catch that pointer that returns back from this function. And if it is still confusing, don't worry, let's first proceed ahead and you'll get a hang of it. So let's now start with the step number 1. So over here, what are the values that we have? We have R equals to N1, correct? We are passing N1 over here, and int V is equal to 40 that we are passing. So val over here is 40 that you want to delete, correct? Alright. So step number 1, we check if R equals to null, then return R. So this is the base condition from this recursion when you want to exit outside. So right now R is N1, which means R is not null. So you'll proceed ahead, you'll go to step 2. In step 2, you are checking else if the value V, is it less than R of value? What is the value V? V is 40. Is 40 less than R of value? R, we are saying is N1. N1 has the value 30. Is 40 less than 30? No. So this else if will not be executed, we will not go inside, we will proceed with step number 3. Over here, we'll check if V is greater than R of value. V is 40, we just said that. Is 40 greater than R of value? R of value is nothing but N1's value because R is equal to N1 over here, right? What is there inside N1? It is 30. Is 40 greater than 30? Yes. So this condition has become true. So we will go inside else if, that is the third else if. We have 3.1. We will say R of right equals to delete node R of right comma V. Okay, so now we are giving the first recursive call. So from the first delete node function, we are giving one more function call, which is the second function call. And over here we are passing r of right, you can see r of right, and this v, which is 40, is going to be passed as it is. So over here you can see the second function call, which is given by r of right. R is nothing but n1. In the first function you can see it is n1, correct? So r is nothing but n1's right, correct? Let me write n1 over here. So this r is nothing but n1, and when you say r of right, it means n1's right will store the address which will be returned by this second delete node function call. So this second delete node is called from the first delete node. So the first delete node will go in a pause state, and it will go in a pause state at step number 3.1. And r of right is nothing but n1's right, correct? What is there to the right of n1? We have n4. So now n4 will be passed over here. This v is going to be nothing but 40 only. So it's going to be passed as it is. And now again we will start with the execution of delete node operation from the start. So let's do that. The first delete node is paused. The second delete node has started its execution. Over here, the first argument r is equal to n4. The value v is nothing but 40. So again, step number 1, is r equals to null? No, because r is n4. So we'll go to step number 2. We'll check if v, which is 40, is it less than r of value? R right now is n4. n4's value is also 40. Is 40 less than 40? No. So step number 2 will be excluded. It will not go inside. We will go to step 3. We'll check if v, which is 40, is it greater than r of value, which is again 40? No. 40 is not greater than 40. So again, this will not be executed. Now this means that we've arrived with the matching value. So you can see we have a else, and in comments I've written if value matches. So if first 3 conditions doesn't execute, it means that we found the match. And inside that we have to check whether it is a node with only one child or no child. And of course it is a node n4. It does not have any children. So inside step number 4, 4.1 only will be executed. Let's see that condition. Over here we are checking if r of left. R is nothing but n4. So right now r is nothing but n4. So r of left, which means n4's left, is equal to null. Yes. Is there anything to the left? No. Which means it will always have null programmatically. So in that case we will go inside. We will say temp equals to r of right. So temp will be created. We will say r of right. R is nothing but n4. What is there to the right of n4? We again have nothing, which means we will have null programmatically. So temp will store null. Then we will say delete r. R is nothing but n4. So we will completely erase off this node entirely. So when you delete that, we will have nothing over here. Then we will say return temp. Temp was null. So temp equals to null will be returned back. Now when you say return temp, this second delete node will stop its working because we are saying a return function, and when you write a return instruction, you'll come outside the function and you'll return back to the calling function. Who called this delete node? It was called by the first delete node, right? So you'll return null, and it is on the RHS, so it will be stored on the LHS as r of right. So this r of right, you can see I've written n1. So n1's right will have null. So initially n1 had n4 to the right, but now n1 will have nothing to the right. So this link will be broken, and programmatically it will have null, which will be stored as the right value or right child of n1. Correct? So when you come back from this delete node, basically what you're doing is you're coming back to the calling function over here, and now the first function, that is this delete node, will resume its operation from 3.1. Correct? So when the first delete node operation resumes from 3.1, let's erase this pause sign. We were over here, okay? The r was equal to n1 for the first delete node, and the v was equal to 40, correct? We've resumed from 3.1. So over here you can see this is a if, else if and else control statement. So if this else if was executed, then this else will not be executed. So after 3, you'll directly jump to step 5. Do we have a step 5? Yes. Remember that this is a AVL tree delete node operation. So after step 3, we have step 5. So let's see what step 5 is. I'll close these 4 steps because these 4 steps are done, and after 3rd we will directly jump to step 5. we still have few more steps of the AVL tree rotation operation, right? So let's see those steps. Alright, so after step 3 we will directly jump to step 5. Now step 5 we will start with the AVL tree code part where we calculate the balance factor, right? So R is nothing but N1 over here right now. So this is nothing but R. So balance factor, we will say get balance factor. Now, what is this balance factor function? Let's see the balance factor function briefly. So this is how the get balance factor function looks like. It is having a return type of int, which means it will return the integer value. That is nothing but the balance factor. It will take a pointer of tree node. Over here we are passing N1, correct? We will check if N1 is equal to null, then return -1. In this scenario it is not null. So we will go in the else part. We will say return height of n of left. N over here is nothing but N1. So N1's left. So height of N1's left, I'll write h over here, minus h of N1's right. Now this height is again a user defined function which we will have to write to calculate the height of a particular tree. Now we have discussed the height function separately in a separate tutorial in detail, so please go make sure and watch that. I'm gonna skip that and assume that you guys have already seen that video and know how to calculate the height and how to, what is the code of the height function. So basically we are calculating the height of N1's left subtree, this is the LST, and height of right subtree, RST, correct? So just by looking at the diagram over here, we will get 1 minus -1, we will get 2, and you are saying return. So you're gonna return 2 from this get balance factor function, okay? And that 2 will be stored in this variable BF. So let's write BF over here equals to 2, correct? So step number 5 is done, and when you get BF as 2, clearly we can see that this tree is imbalanced because it has nothing towards the right. This null is nothing but basically it doesn't have anything, so I can completely erase it off. Programmatically it will have null as the right child, but diagrammatically this is how the structure would look like. Now we will go to step 6. In step 6 we will check if BF equals to 2, which is true. So this first part is true. Let's write T over here. And we have an AND clause in between. We will say get balance factor of R of left. R over here is N1. So R of left is nothing but left of N1, which is N2. So we will again call get balance factor for N2. Now looking at this N2, this is the left subtree. It has only one node, so height of left subtree is going to be 0. Do we have anything towards the right of N2? No. So height of left subtree is going to be -1. So 0 minus -1 is going to give you 1. So when you get the balance factor from over here, it will return 1. Correct? So this function will take N2 as the argument and return 1 as the value. Is 1 greater than or equal to 0? Yes. Which means both this first condition, which means this BF equals to 2, and this get balance factor condition where we got the value as 1, both of them are true. So now we will go inside step 6.1. That is the first if condition only got true. And over here you are saying return right rotate of R. Okay. Currently we are executing this delete node. Remember that we have resumed the operation of this delete node, and inside this delete node we are at step number 6.1 now. We are saying return right rotate of R. So what is this right rotate function? So let's see the code for right rotate. And we are passing R, which means we are passing N1. Okay. So over here we are passing N1. Okay. So this is the code for right rotate. Again, it has a return type of tree node star, which means it will return a pointer after doing the rotation. It is taking an argument of tree node pointer, and over here Y is nothing but N1 that we've passed. Okay. Now if you've seen the insertion part, the right rotate and left rotate are exactly the same. You guys can skip to the further part of the deletion. You can skip this right rotate and left rotate code. But for those who haven't seen that, the first step is you create tree node X equals to Y of left. So X will be equal to Y of left. Y is nothing but N1. So this is Y. What is there to the left of N1? We have N2. So X is going to be N2. Then you will say tree node star T2 is equal to X of right. X we just said is N2. Is there anything to the right of N2? No. So this means we will have null over here. and then we'll perform the rotation. We'll say x of right equals to y. So x is equal to n2, correct? This is x. We will say x of right. So right now n2 is right, we don't have anything, but we will say x of right equals to y. Y is nothing but n1. So we will take this n1 and make it right child of n2. Okay, so at this step what we are saying is x of right is nothing but n2's right on the LHS, and on the RHS we are saying y is nothing but n1. So n1 now becomes the right child of n2, and at the last step we are saying y of left, y is nothing but n1. So n1's left equals to t2. T2 is nothing but null. So n1's left will have null. So this link will be broken, correct? So it will have nothing. So I can erase it off for representation purpose. And now you're saying return x. X is, you can see, n2. So basically n2 is returned from this right rotate. Okay, so this is the right rotate function. Similarly we have left rotate. I can show it to you on the screen, the pseudocode for that. Currently, since we are not performing the left rotate, that code is not going to be applicable in this tutorial, but for some other case you can try to dry run the left rotate also. You can see it on the screen. But moving on, we just said return x, which means we just returned n2. So n2 will be returned from right rotate. So we were at 6.1. We say return right rotate. This right rotate returned us the address of n2, correct? So this return right rotate means return n2, and n2 now will be returned from this delete node function, because remember we were at the 6th step of this delete node function. We are still basically executing this first delete node only, and we are at the step number 6.1, and we say return right rotate, which means we got return n2. So n2 will now be stored, n2 will be returned, and it will be stored as obj.root. So obj is the object of AVL tree class, and it has a root pointer which initially had n1, but now n1 is become a right child of n2, and n2 is basically now the new root, right? So this n2 will now be stored as the address in the root pointer. So n1 will be rewritten, and this obj will have a root pointer which will now point to n2. And since this step number 6.1 was executed where we did a return from this delete node function and we came back to the main function, step number 7, 8, 9 and 10 will not be executed because we returned from this function at step number 6.1 itself. So all these steps will not be executed, and we will come back in the main function where the root data member of the obj object, that is the AVL tree object, will now be updated, and it will store the address of n2. Okay, so this is what will happen when you call the AVL tree delete node recursive function. Okay, so this was the complete dry running of AVL tree delete node operation with the entire pseudocode. We also dry run it step by step. We saw the different changes that are happening in the diagram. We also saw the recursion taking place. And now what you guys can do is you can try this same function again on different cases. So what we saw was a left imbalance case, right? Try to take other case and see when this else if will be executed, see when this else if will be executed. We've already seen the 6 different deletion cases. Pick any of the deletion case and try to apply this same pseudocode on that particular case. Take a pencil and paper and at least try to do it once or twice so that you get the full understanding of the entire pseudocode for AVL tree delete node with recursion. Okay, so now the only thing left out is to convert this entire AVL tree code, that is the pseudocode, into C++ code and see a program. So let's jump to the dev C++ code ID and try to practically implement this pseudocode. Okay, so as you can see on the screen, I have already written quite a lot of code. This is the dev C++ ID where we write C++ code. We've created the tree node class. We've created the AVL tree class. Inside that we have the tree node root pointer. We have the basic functions, and don't worry guys, I'm going to be sharing this entire code with you guys. So quickly go to the link in the video description on our official website, that is simplesnippets.tech. Over there we have this article where you'll get the entire code. Try to dry run it yourself at least once. Even if you're copy pasting it, please dry run it yourself. In fact, the best thing is you should type it yourself at least once. So this is the height function which I was talking about. We've already done this in binary search tree implementation. The height function for binary search tree and AVL tree is going to be exactly the same. That's why I did not cover it over here. Then we have the get balance factor function. we have the right rotate, we have the left rotate, then we have the insert node operation which we did in the previous tutorial. So you'll get the code for this also. Then we have the minimum node value which is required for delete node, because when you delete a node which has 2 children, then you have to apply that minimum node value methodology which we've discussed in the deletion of binary search tree node. So that is going to be exactly the same in AVL tree. So please make sure you watch the delete node operation for the binary search tree to understand the first 4 steps thoroughly, because we've discussed all the different cases over there. Over here we only took a simple case where we deleted a node which did not have any child, right? So that was a simple case. So when you go below, this is the commented code which did not work properly. Let me just erase it out. So this is the code for the AVL tree part. Okay. So till here we are doing the deletion which is exactly the same as the binary search tree deletion. After that we have the code for getting the balance factor, and then we have if, else if and else if, the 4 different conditions which were handling the 6 different deletion cases, and then we have the return R. Okay. So if you scroll down, we have this print 2D function which will do nothing but the printing of the entire tree onto the command prompt in a graphically intuitive way. We have the recursive search also, which is exactly the same like we have in binary search tree searching. So I'm not covering that. I've just written the code over here. You can, go and check out the search from binary search tree. And this is where the AVL tree class ends. And in the main function, we create the object. We create a menu driven program. So we take the option number, and depending upon whether the user enters 1, 2, 3, 4, 5, 6 and 0, we will call that respective operation. So if the user enters 1, we will do the insertion. If the user enters 2, we will do searching. If user enters 3, we will do the deletion. Okay. So this is the option number that the user enters. Then we create a new node pointer which points to the object which is created in the heap memory. So this methodology is used to create an object of type tree node in the heap memory. And this new node is nothing but a pointer which points to that particular object. Okay. Now this is done because when you create an object using the new keyword onto the heap memory, it will have global scope, which means that it will be there in the heap memory throughout the program execution till you explicitly delete it. Okay. And that is what we want, because we are running this program over and over again using the menu driven functionality of a do while loop. So you can see there is a do while loop over here which is running over and over again. And in the switch case, we are passing the option number depending upon whether the user enters 0, 1, 2, 3, etc. We are using the AVL tree insert, search, delete, print. We are also getting the height of the tree, and we are clearing the command prompt. And if user enters something weird, we are saying enter proper option number. And then the do while loop condition is if option number is not equal to 0, keep on running this while loop. So let's save this and let's go to execute, compile and run. Let's see if things work. Alright, so our program is working fine. Let's see if the delete also works. Let's first insert some values. Let's say I'm inserting 50. Again, I'll insert, so option number 1, I'll insert 40, hit enter. I'll insert again and I'll insert 30. So if this was a regular binary search tree, the structure would look something like this, which you can see on the screen, 50, 40 and 30. But since this is a AVL tree, in the insertion of AVL tree also we do the balancing. So when you insert 30, the tree becomes imbalanced, right? It becomes left imbalance. So you'll do a right rotate, and then the 40 will now become the new root node. So let's enter 30, and now let's try to print the tree. So option number 4, if you hit enter, you can see 40 has now become the root node, right child is 50 and left child is 30. So let's enter one more value as 20. And now let's print the values. We have 40, 30, 20, so and 50. Now this tree is rotated in minus 90 degree in anti-clockwise direction, but it still represents proper tree. And now let's try to delete 50. So when you delete 50, again it will become a left imbalance. So we will do a right rotate, which means 30 has to be the new root node, right? So let's go to delete. Option 3 is the delete node. Hit enter. It is asking the value of tree node that you want to delete in the AVL tree. We want to delete 50. When you hit enter, you get value deleted, which means program ran properly. Now let's see and print the tree. When you delete 50, 30 should be the new root node. The right child of 30 should be 40 and left child should be 20 as it is. When you hit enter, there you go guys. The tree is now balanced again. 30 is now the new root node. The right child is 40, left child is 20. So this means our delete node operation is working perfectly fine. You guys can run this program and go ahead and enter as many number of nodes as you want. Try to delete as many number of nodes as you want. See if everything is working fine or not. And this is where we've successfully implemented the delete operation in an AVL tree. Okay, so I'm going to conclude this video over here. I hope you've got a clear understanding of the implementation side of deletion in an AVL tree along with the different rotations, different deletion cases. If you've understood this video, please give this video a like. Let me know in the comments how this video was. Definitely share this video with your friends. The practical aspect is also important, guys. And I know this video was lengthy, but if you've made it so far, I'm pretty sure you guys have found some extra value in this video. So I highly recommend that you subscribe on this channel for more such video tutorials in future. If you have done that already, please turn on the notifications. And I'll see you guys in the next one. Peace.